So we saw this slide in an earlier session, and these Lewis symbols are really important for actually being able to work out how a particular atom is going to form covalent bonds to fill its valence electron shell and become stable. So I've put a green box around the most important atoms here because these are the ones that we're going to see most in organic chemistry and throughout the whole unit. So in this representation, each dot around a chemical symbol represents a valence electron. So you can see some of the ones that we need to be aware of. We've got carbon in group 4, so it's got 4 dots because it's in group 4. Nitrogen has 5 valence electrons, group 5, oxygen 6, and so on. So one thing you need to be aware of when you're working out the group number and then how many valence electrons there are. So I'll just use an example of X. So say X has 6 valence electrons. So if we knew X was in group 6, then we'd try and place those valence electrons. So I'll draw it as a Lewis dot symbol, so each dot represents an electron. So there's 4 positions in the outer shell or valence shell called orbitals, which can house electrons. So each orbital has to have one single electron before any can become paired. So we've used 4 of the 6 electrons here that are in the valence shell. So where do I place the next 2? Well, it's kind of arbitrary, but 2 of these orbitals are now going to have 2 electrons. So now we've got a distinction between paired electrons and unpaired electrons in this outer valence shell. So you can see up the top here we've got 2 paired electrons, 2 pairs of electrons, and then the other ones are single electrons. So which of these is going to contribute to the ability of X to form covalent bonds with other atoms? It's going to be these ones that are unpaired, right? Because they need to become paired to be stable, to get 8 electrons in that outer shell. So essentially, not only do you need to know the number of valence electrons, you need to be able to draw these structures to actually work out how many unpaired valence electrons there are. So for carbon, we're going to look into that in a fair bit more detail, but carbon's pretty simple because it's always got 4 valence electrons when it's by itself. So that means carbon has 4 unpaired valence electrons. So if we put one of the valence electrons in each of the orbital positions, every single one of them is unpaired. So this means that every single one of those valence electrons will contribute to the ability of carbon to chemical bond, or specifically covalent bond to other atoms. And that's what makes carbon so unique, the ability to form covalent bonds to 4 other atoms. So remember, the Lewis dot symbols tell us how many bonds something needs to form to get up to that 8 electrons, so which is the electron octet. So once you've worked out the number of unpaired valence electrons, that's the number of bonds the atom needs to form. So because the carbon atom contains 4 unpaired valence electrons, that means it can form 4 covalent bonds. Nitrogen has 1, 2, 3 unpaired valence electrons, therefore it can form 3 covalent bonds. Oxygen has 2, and fluorine and hydrogen both have 1. So these are common atoms that we're going to see a lot in compounds, and it'll be good to know how many unpaired valence electrons each one has, because that allows you to know how many lines or how many covalent bonds these atoms have to have in a structure. And to draw your structures correctly, you need to know these rules. So here we have a representation of 4 atoms. So we've got the atoms represented with their Lewis symbols. So each of these dots here, or circles, is an electron. So we can see nitrogen is a combination of paired electrons and unpaired electrons in its valence shell. So we've got the pair of electrons at the top and then 3 other unpaired electrons in that outer valence shell. Hydrogen actually only has 1 electron, so we see a single circle associated with that. So we talked about earlier how atoms need to come together to become stable, and they do this by covalent bonding. So let's see what's going to happen to our nitrogen and 3 hydrogens. So we can see here that the hydrogens and the nitrogen have associated together, allowing the unpaired valence electrons to actually form pairs between the different atoms. So we can see for each one, the hydrogen and the nitrogen unpaired valence electron have come together, and the red line between these represents a covalent bond where the electrons are actually going to be shared between the two atoms involved. So these two electrons here are going to be shared between this nitrogen and this hydrogen, just like these two will be shared between this hydrogen and this nitrogen. So instead of drawing it out like this every single time, showing the electrons as circles, where we have two electrons being shared representing a covalent bond, there's actually a simpler representation that we usually write it in. So instead of having these circles representing the electrons, a covalent bond is just shown as a line between two atoms. So you can see that each of these electron pairs here is just represented as a line. So we've got the three covalent bonds between the nitrogen and the three hydrogen atoms, just like we had on the left-hand side here. So on the right-hand side, this is the common representation that we're going to see our compounds represented in if all the bonds are drawn out. So NH3 is actually the covalent compound ammonia, which you might have heard of. It's in some household cleaning items. So how do we know, or what governs whether atoms are going to behave in this way? Essentially, it comes back to the octet rule that we touched on in an earlier session. The ability of atoms to get the right number of valence electrons to be stable. So they're trying to get up to that 8 valence electrons in the outer shell. The exception to this is hydrogen that only needs 2 because it only has one shell. So atoms will actually lose, gain, or share their electrons to try and get the right number. The lose or gain part comes from ionic bonding, but we're more focused on covalent bonding, which is all about sharing, because that's what happens in organic compounds. So once an atom has 8 electrons in its valence shell, we can say it's satisfied the octet rule, and that makes it stable. So as I talked about earlier, there are some elements that naturally have 8 valence electrons. These are the noble gases, for example, neon. This means they're very stable and actually don't need to form covalent bonds with anything else because they're already in this stable state. Whereas something that's not a noble gas, like nitrogen, you can see here, we don't have that full valence electron shell. The number of dots around the outside here doesn't add up to 8. So what has to happen is the nitrogen actually needs to participate in bonding with other atoms, just like I showed you on the previous slide, to get up to an 8 electron arrangement. So the new electrons that it's now sharing are actually represented as these red dots here. So you can see by covalent bonding, the nitrogen's actually able to get 8 electrons in its valence shell and therefore mimic the electron arrangement in the noble gas. So essentially what atoms are trying to do by forming bonds is to become really stable, just like a noble gas. And they can do this by forming chemical bonds with other atoms. So this goes back to the idea that atoms are more stable if they're in a compound than if they're by themselves. So why is that? Well, it's because if the atoms are in a compound, then they're going to have undergone the bonding to allow them to have the right number of electrons in the valence shell to be stable. So that will mean they've satisfied the octet rule. So we talked about the different types of chemical bonding in earlier sessions as well. So we can either have electrons being donated from one atom to another, and that actually causes the atoms to become ions. And this is what happens in ionic bonding. So remember, ionic bonding is present in ionic compounds. We saw an ionic compound earlier, NaCl, which is where the sodium becomes positively charged by losing an electron, and the chlorine becomes negatively charged by gaining an electron, and then we have the attraction between that positive and negative. But the bonding we're focusing more on in this session is the covalent bonding, and this is where two atoms come together and share their unpaired valence electrons to allow the valence electron shell of each atom to fill up. And this is the type of bonding we see in organic compounds. So let's talk a little bit more about the covalent bond. So what is it? As I've been talking about, it's the sharing relationship between two atoms where they're each contributing one electron to a shared pair of electrons. So we've got a few different ways of representing this. So drawing out the electrons as circles here, we can see that oxygen is actually sharing one of its unpaired electrons with this hydrogen and also with the other hydrogen here. So each of these electron pairs in the red circle is actually a covalent bond. But a simpler representation that we're going to see more often is where we have lines between the atoms representing that electron sharing relationship, which is the covalent bond. So the magic of this covalent bonding is that the atoms will actually form the right number of bonds to actually allow them to have full valence electron shells, and that makes the compounds very stable. And why this is so important is because these shared pairs of electrons that result from the covalent bond actually count towards the electron total for both atoms. So this electron pair in the red circle here counts for hydrogen's electrons and for the electrons in the oxygen valence shell. That's why they're called a shared pair of electrons. They count for both atoms. So when oxygen is a part of the water molecule, it actually has 8 valence electrons. So we can count those. We've got 1, 2, 3, 4 up top here, and then we've got 2 electrons from each of these covalent bonds. So that's 4 up top, then 2 plus 2 equals 8, satisfying the octet rule. And each hydrogen also satisfies its need for a full valence shell by accepting an electron from oxygen. So for hydrogen to have a full valence shell, it just needs 2 electrons because it only has the one shell. So essentially it all comes back to this idea that the atoms will form as many covalent bonds as they need to get a full valence electron shell, which is, for most atoms that aren't hydrogen, 8 valence electrons. So there's a useful rule that we can use to work out how many covalent bonds something's going to form. It's essentially the number of unpaired electrons the atom has is equal to the number of covalent bonds that the atom needs to form to get to the electron octet. So let's have a look at our example of water again. So we've got 2 different atom types. So we've got oxygen, which is in group 6 and contains 6 valence electrons. So based on our knowledge that it has 6 valence electrons, we can draw our Lewis symbol where we've got 2 pairs of electrons in 2 of the orbitals, and then there's 2 unpaired electrons. So because we've got these 2 unpaired electrons, if we look at this rule, the number of unpaired electrons equals the number of covalent bonds. So that tells us that the oxygen has the ability to form 2 covalent bonds. And that's what we can see in this structure here. Oxygen is forming 1 covalent bond with hydrogen this way and 1 with another hydrogen this way. So that's going to satisfy oxygen's need to get up to 8 electrons. Let's do the same for hydrogen. So hydrogen is in group 1, so it contains 1 valence electron, and that valence electron is unpaired. So what does that tell us about the hydrogen's ability to form a covalent bond? Well, the number of covalent bonds equals the number of unpaired valence electrons, so the hydrogen will form 1 covalent bond to be stable. And that's what we can see for each of these hydrogens in water. It's forming 1 covalent bond with the oxygen atom. So by forming the water molecule, both oxygen and the hydrogen atoms have full valence electron shells. So you can see here that oxygen has 8 valence electrons by forming an additional 2 covalent bonds, and each hydrogen atom has 2 valence electrons by forming 1 covalent bond. So they've all got full valence electron shells, which is what you see for all organic compounds. So if the atoms come together in a specific way in an organic compound, that means that they're going to have these full valence electron shells and be stable. So an interesting question here that's posed: how can individual atoms increase their stability? So what would an atom do to become more stable? So it all comes down to the atom's ability to form chemical bonds to get a full valence electron shell. So essentially, to achieve stability, the atom has to form the number of chemical bonds it needs to fill its valence electron shells. So for oxygen, that was forming 2 covalent bonds. For hydrogen, it was forming 1 covalent bond. So essentially, depending on which atoms are involved, we have them forming specific numbers of covalent bonds to make sure all the atoms in the compound are going to have the right number of bonds to fill their valence electron shell. So if we look at the structure on the right hand side here, we can see that each of the atoms involved actually has the right number of covalent bonds. And that's how we know that our structure is correct, because every single carbon forms 4 covalent bonds. Because remember, it had 4 unpaired valence electrons that needed to be paired via the covalent bonding. So if we look at this carbon atom here, we've got 1 bond to 1 hydrogen here, bond number 2 to another hydrogen, 3 to a third hydrogen, and the 4th bond is actually to another carbon. So you could do this for every single atom in the compound, and it would come out as the right number of bonds to fill the valence electron shells, with each carbon having 4 bonds and the hydrogens each having 1. So some questions to consider and to help you cement what we've just been through in the lecture here. So I'd advise you to pause the lecture at this stage and spend 5 or 10 minutes having a go at these questions, and then you can continue the recording where I'll go through a little bit of an explanation. So remember, it will be really helpful to your learning for you to have a go at these questions yourself. The learning will be limited if you just continue watching before attempting these questions. Alright, so question 1. What groups are hydrogen and carbon in on the periodic table? So there's a couple of ways you could have got this answer. If you had your periodic table, you could have looked it up, or you could have just gone a couple of slides back to the Lewis dot symbol slide. So we saw that carbon was in group 4, so that's IV in the Roman numerals. And hydrogen is in group 1. So remember, this is going to be important because we can actually work out how many valence electrons each of these atoms has by using these group numbers. So how many valence electrons do hydrogen and carbon atoms contain? So based on the group numbers that we just found here, we can actually work this out, because remember, the group number equals the number of valence electrons. Okay, so that means for carbon, it was in group 4, so it's going to contain 4 valence electrons. What about for hydrogen? Well, hydrogen, what group was it in? It was in group 1, so that means it's going to have 1 valence electron. So now that we know how many valence electrons they have, we can draw the Lewis dot symbols for each. So let's start with hydrogen because it's nice and simple. It's only got 1 electron. So you could place this electron at the top, bottom, or left or right. I like to put it on the right hand side here, but because there's 4 orbitals, in theory it could be in any of the 4 positions. What about carbon? It's got 4 electrons. So remember, there's 4 different positions, 4 different orbitals that the electrons can reside in, one at the top here, and each side and the bottom. So the rule is that we put 1 electron in each orbital before any of them can become paired. So because carbon has 4 valence electrons, that means each position gets 1 valence electron. So based on these Lewis dot symbols, we can actually work out how many covalent bonds each atom must form to get a full valence electron shell. And remember, the number of valence electrons is equal to the number of unpaired valence electrons, is equal to the number of covalent bonds. Okay, so let's have a look at how many unpaired valence electrons each of these has. Remember, the number of valence electrons might not always be the same as the number of unpaired valence electrons. Some of the valence electrons can be paired. Not in this case, but keep an eye out for that. So for hydrogen, we've got 1 unpaired valence electron, and for carbon, we've actually got 4 unpaired valence electrons. So what does this tell us about the number of covalent bonds each forms? Well, because carbon has 4 unpaired valence electrons, that means it's going to form 4 covalent bonds. And with hydrogen, it has 1 unpaired valence electron, therefore it's going to form 1 covalent bond. So why are these atoms forming this number of covalent bonds? Well, it's to make sure that all of the electrons in their valence shell, their outer shell, are going to be paired. So that was a really nice way of summarizing what we did in the first part of this session. Essentially, we're going back to this idea here that atoms are forming covalent bonds to allow their valence electrons shells to be filled, and also this allows the atoms to become stable. So to summarize what we saw in the previous question, how many covalent bonds must carbon and hydrogen form to be stable? And we can actually work this out by looking at the structure on the right, but also from the questions we just answered. So because carbon is in group 4, it contains 4 unpaired valence electrons, and therefore each of those unpaired valence electrons can be part of a covalent bond. So there's 4 covalent bonds needed for carbon to be stable. So you can see each of the carbon atoms here are forming 4 covalent bonds, so they're satisfying their octet rule. Whereas for hydrogen, it's in group 1, so it contains 1 unpaired valence electron, and that means that each of those hydrogens can form 1 covalent bond, as you can see here in the right-hand structure. Every single one of the hydrogens has just 1 line coming off it, indicating that it's forming 1 covalent bond.